Edward Hoffman of the United States Naval Academy at Annapolis, and he will talk to us about multiple zeta values and quasi-symmetric functions.
Well, thank you, organizers, for inviting me. So let me first give you the outline here. First, I'll just make clear the notation, and then I'll tell you a little bit about the quasi-symmetric functions.
You switched on.
Quasi-symmetric functions. And then I'll get around to the real point of this talk, which is thinking of multiple zeta values as images under a homomorphism from the quasi-symmetric functions to the reals. At first, we won't be able to define it on quite all of the quasi-symmetric functions, but then I'll explain that algebraically you can extend it. And then it's an extension with a parameter, which I'll show you. If you're thinking in terms of generating functions, there's a nice choice. You can choose the parameter to be Euler's constant. This turns out to be a nice choice. Then I'll touch on some relations between this homomorphism and topology. And then I'll talk about some more algebraic things. First, using the Hoff algebra structure, the quasi-symmetric functions, to give a convolution factorization of this extended homomorphism. And then also some recent work of mine on multiple zeta values of even arguments. So just to fix notation, we all know what this means, but I'm using the convention which David used yesterday, that the exponent on the biggest number comes first. So my multiple zeta values don't converge unless the first number in the exponent string is bigger than 1. And of course, if you're just at depth 1, we know all about that. That's the classic Riemann zeta function, and Euler proved this nice formula about the even values, which I'll have occasion to use later. But work on the sort of general depth ones didn't start until really the late 1980s, and a few of us here are the old timers from that subject. Some of you probably weren't born yet, but all right. So now let me move on and talk about the quasi-symmetric functions. So I'm working in formal power series and countably many indeterminates. If I work with the ones of bounded degrees, this is a graded rational algebra. And a quasi-symmetric function is one in which the coefficients of two monomials with the let me see if I can find the right. With the same exponents agree if these subscripts are in increasing order. So for example, this thing at the bottom is a quasi-symmetric function. It's the sum of all the monomials xi squared xj, where I is smaller than j. That's a quasi-symmetric function. It's not a symmetric function. So actually, these are usually attributed to Ira Gessel, although they may have actually appeared earlier. Anyway, it's fairly obvious if you think about it that you can get a basis of monomial ones by just quasi-symmetrizing a monomial. And so these are indexed by the string of exponents, where you arrange these in increasing order of the subscripts. So the difference between this and the symmetric function is here the order matters. So combinatorialists call this a composition. It's an ordered partition. Now, of course, if you forget the order in a composition, you get simply a partition, an integer partition. And everybody knows that you have monomial symmetric functions, so that quasi-symmetric function I had on the last slide is really what I call capital M sub 2, 1. And if you add capital M sub 2, 1 to capital M sub 1, 2, you get the monomial symmetric function, little m sub 2, 1. Okay, so that's the notation. And now let me say, these are elementary facts, but I just recall them to fix the notation. So you have the sort of standard elementary complete and power sum symmetric functions. The elementary ones are the ones that correspond to the partition that's just all ones. Of course, if all the things in the string are the same, it doesn't matter whether you order it or not. So those are the elementary symmetric functions. You can get a basis for the symmetric functions by just using products of elementary symmetric functions. The complete symmetric functions are just the sum of all the monomial symmetric function or monomial quasi-symmetric functions of a given weight. And then you have the power sums, which just correspond to partitions or compositions of one part. So this is just, a piece of k is just the sum of the nth of the kth powers of the infinitely many variables, x1 to the k plus x2 to the k plus, and so on. Okay, and of course, you can get bases by taking products of elementary symmetric functions, products of complete symmetric functions. You get a basis by taking products of power sums, but here, if you express everything in terms of these, you have to introduce denominators. So these are integral bases. The elementary and complete, the power sums are rational bases. All right. Now, the algebraic structure of the monomial of the quasi-symmetric functions, if you think of them in terms of this monomial basis, is precisely what David called the Stuffle algebra last time, and I call the quasi-shuffle. So just, it's easiest to illustrate by way of example. If you multiply m1 by m12, you have all the three terms in which you shuffle the 1 in there. Of course, you could shuffle it in this spot or this spot, so these two are the same, and then you could shuffle it in the last spot. Then you have the ones where you actually combine some of them. So the 1 could be combined with the 1 here to give you the m22, or it could be combined with the 2 to give you the m13. And in general, the number of terms in the product of two monomial quasi-symmetric functions is this rather alarming sum of binomial coefficients. Of course, in the shuffle algebra, it's just one binomial coefficient. Here you've got a whole sum because basically this is a multinomial coefficient, actually. So this is this factorial divided by the factorial of that times the factorial of that times the factorial of that. So, for example, if you multiply m sub 1, 1 by m sub 2, 1, you get 13 terms, which I've listed here. So I've actually done a lot of calculations with these over the years. In a way, they're sort of easier to work with than the ordinary monomial symmetric functions because although there's more terms, these coefficients are sort of a little easier to see. But anyway. Let me say a little bit about the algebraic structure. So, at least rationally, you can describe. Rationally, you can describe the algebraic structure as follows. First, there's a lexicographic order on compositions, like so. And now you define a Linden composition to be one that's strictly less than any of its proper right factors under juxtaposition. So I said all those words right, but if you haven't worked with this before, you have to fiddle with this for a while to understand it. But, okay, that's the definition. Yes. So the theorem about this was proved by Reitnauer and Malvenuto in 1995, which is that the quasi-symmetric functions are a polynomial algebra on the M sub I with the composition I being Linden. So this actually is a polynomial algebra. Essentially, at about the same time, about a year later, I reproduced this result, except that I didn't know I was working with quasi-symmetric functions. I thought I was working with multiple zeta values. So this is sort of some of the ancient history. Now, the only Linden composition, it follows from this definition here, the only Linden composition that actually ends in 1 is just 1 by itself, which means that one of these polynomial generators is m sub 1, and that's algebraic. Since this is a polynomial algebra, that's algebraically independent. If you call q sim sup 0, the one generated by all the other m sub I Linden, you can express this as a polynomial algebra over this one generator. And that's of importance because essentially now when we talk about the map to the quasi-symmetric functions, this is the one that doesn't converge, basically. Okay, so before I get to that, let me just mention a convenient algebraic construction, which is I'm going to define a linear function a sub minus, and I can define it on just the monomial quasi-symmetric functions. And what it does is, if you've got this string and it ends in 1, you just kick that 1 off the end. And if that last thing isn't a 1, you just send it to 0. Okay, and what does it do to M sub just 1? Well, it sends it to M empty set, which is I interpret as being the unit element 1. So it sends that one to 1. And it takes a little fiddling, but it's not deep. This is a derivation on the quasi-symmetric functions. You can prove that fairly easily just from using the quasi-shuffle product. And furthermore, I've designed it in just such a way that its kernel is this q-sim sup 0, the ones that end in things bigger than 1, because they all go to 0. So if you think of the quasi-symmetric functions as being the polynomial algebra over q-sim 0 generated by M1, this operation just differentiates with respect to M sub 1. Okay, so back to multiple zeta values, remember those. Here's the function that, the homomorphism that's going to be sort of the main topic of this talk. There's a homomorphism from this q-sim 0 to the reals given by, you take zeta applied to a monomial quasi-symmetric function, you reverse the order, and that's that multiple zeta values. Of course, q-sim 0, this last thing's bigger than 1, so this is bigger than 1, and therefore it's a convergent multiple zeta value. Now that's actually induced by the map that sends this basic variable xj to 1 over j. Of course, I suppose you could take the fact that I have to do a reversal here as evidence that maybe I've been using the wrong convention all along, but okay, I'm too set in my ways to change. So. Okay, so notice the effect of this is that the power sum symmetric functions just go to the ordinary multiple zeta values. And the intersection of the q-sim 0 with the symmetric functions is what I call sim 0. It's really just the subspace of the symmetric functions generated by all the power sums except P1. Now, the thing that's nifty about this is, since I don't have M sub 1 defined, and because it's algebraically independent, I can send it anywhere I want. So I could just send it to a parameter, and so this gives me an extended thing that goes from quasi-symmetric functions to the real numbers with this parameter u, with M1 going to u. And then the fact that this A minus I introduced before is this derivation actually tells me that I have a commutative diagram here. So this map, this is the extended zeta map horizontally. Downward I have A minus, and in the image that's just differentiation with respect to u. Now, you can, of course, send u, if you want to actually get a map to the reals, you can send u wherever you like, but it turns out there's actually a particularly nice choice. You can send it to Euler's constant, and this actually is a nice choice for reasons that involve some generating functions, which I'm about to introduce. So you'll remember we had those three bases for the symmetric functions, the elementary, complete, and power sums. Well, here are their generating functions. And again, this is well-known basic algebra material for anybody who knows about the symmetric functions. But OK, the generating function for the elementary symmetric functions is just this infinite product. This other infinite product is the generating functions for the complete symmetric functions. And notice there's a symmetry if you replace t with minus t and take reciprocals. That takes this generating function to that generating function. And then the logarithmic derivative of the generating function for the complete symmetric function is the generating function for the power sums. Okay, so this is all well-known stuff, but the thing is, because these are all related by these simple transformations, basically, if you can figure out what a homomorphism does to any one of these generating functions, then you know what it does to the others. and I will make use of that shortly. Okay, such as on this slide. So why is Euler's constant a good choice to where to send M1? Well, basically because there's this power series expansion for the psi function, the logarithmic derivative of the gamma function, in which the constant term is just Euler's constant. So if you make your image of M1 or P1 to be Euler's constant, then this thing on the right is just minus the image of the generating function for the power sums. Which means that, well, okay, if it does this with the, this is the logarithmic derivative of the gamma function, so it must send the generating function for the complete symmetric functions is just the gamma function of 1 minus t. So the nice thing about this choice is if you send P1 to Euler's constant, you now send the generating function for the complete symmetric functions just to the gamma function, or the gamma function of 1 minus t. And of course, we now also know what you do with the generating functions for the elementary one. It's replace t with minus t and take reciprocals. Well, I had some fun with this back in the paper I published in 1997, because now you can use this to get a nice formula. It turns out that if you take the generating function for all the so-called height 1 multiple zeta values, that's the one in which all the exponents are 1 except the first one. You can get a 2-variable generating function. It's purely a theorem in analysis that this is expressible in terms of the gamma function. Well, the beauty of this is in view of the result in the previous slide, that means I can now think of this whole right-hand side as just the image under my extended zeta function of this combination of generating functions of the complete symmetric functions. And see, the thing is that this generating function for the complete symmetric functions, it's the logarithmic derivative of the power sum, so I can write it as an exponential like that. And I can pull out that first term. This is the only place where P1 appears. And that's going to cancel out in this combination, which means that now this thing is just a formal identity in symmetric functions. I apply my extended zeta function here, and so I have this height 1 function, height 1 generating function, expressible entirely in terms of just zeta values, zeta 2 and higher, because things cancel, all the P1s canceled out.
And this is called the Euler beta function.
Yeah, it's the beta function, but you don't so much need that. The thing is that this means that any of the coefficients in this series, any of these height 1 multiple zeta values, is expressible in terms of just ordinary values of the Riemann zeta function. And that's interesting because, okay, it was already apparent that if you had a multiple zeta value that was symmetric, was the image of one of these quasi-symmetric functions that was symmetric to begin with, of course it's going to be expressible in terms of just the ordinary zetas. But these things are manifestly not symmetric functions. And yet they're still expressible in terms of these zeta i's. Now, to be honest about, okay, so I had this in my 97 paper. That to be honest, Borwein, Broadworth, Borwein, and Bradley, I think it was, had already proved this by a purely analytic argument about a year earlier. But the nice thing about this proof is it brings up this interesting combinatorial thing about thinking of these as images of quasi-symmetric functions. And it turns out that although I thought I thought I had sort of the nicest generating function results possible, actually this had a long way to go yet, as it turned out. So shortly after I'd actually published the paper that had this, there was a lot else in that paper, but it had this generating stuff, function stuff. I happened to be just looking at journals, and this is something you could hardly do these days because we tend to read stuff online. But I was just looking at journals in the library, and I saw this paper about mirror symmetry, and something looked oddly familiar about some of the formulas of that paper. And I kept coming back to it, even though I knew nothing about mirror symmetry at the time. And then I realized that, well, it was this function. It was this function here that was coming up. So let me say a little bit about this. This was a remarkable serendipitous discovery, but now I have to actually say a little bit of background about the results I'm going to talk about. So now I will say a little bit about topology, although I'm going to keep it to a minimum for time reasons. So, okay, a genus in the topological sense is you can think of as a function on manifolds that has this takes Cartesian products to products, and you can get one in particular if you're working in the class of almost complex manifolds by taking a so-called multiplicative sequence of Chern classes and evaluating it on the fundamental class. Now, what does multiplicative sequence mean? Well, multiplicative sequence means that if you write your image of the sort of formal Chern class, total Chern class, as, okay, homogeneous components here, the product of two of these is k of the product. And that's actually means that you could associate to any formal power series one of these so-called multiplicative sequences by just this trick of taking the homogeneous terms and thinking of them as elementary symmetric functions and new variables, and then if you got the sum of all the elementary symmetric functions, you can just write it as a formal factorization here, which means if you know what this multiplicative sequence does to 1 plus t, you know what it does to everything. And that means that, so this was all worked out by Hirzebruch in the 50s. If you take the multiplicative sequence belonging to the gamma function, or not quite the gamma function, but gamma of 1 plus t reciprocal, it turns out that this was the multiplicative sequence that I happened across in the journal, in a paper by Lidgeber. And, well, okay, I knew about that function, and I figured, oh, gee, I guess I can figure some things out about that in terms of multiple zeta values. So this paper that I happened across by Lidgeber was about mirror symmetry, and this involves Calabi-Yau manifolds, which we can think of as simply connected Kähler manifolds with vanishing first Chern class. Here's a slide about string theory, which I'll go quickly through so that David doesn't frown at me. But actually, I think Calabi-Yau, this Calabi-Yau story is a case where, although perhaps mirror symmetry hasn't proven itself particularly useful in physics, it's certainly been useful in mathematics. So this is a big success. But anyway, the thing is, the basic context is that in the process of doing this, looking for Calabi-Yau manifolds in these sort of 10-dimensional things, which factor is sort of 6-dimensional things across R4, they found they had sort of pairs of manifolds, topologically quite different, and yet they seem to relate to the same physics, or what string theorists think of as physics. But anyway, the problem is that you can read papers on mirror symmetry for a while, and the problem is that lots of people have sort of come up with their formulation of what mirror symmetry is, but it's not necessarily the same between two authors. So what it amounts to is there isn't really a completely general construction of what the mirror pair of a Calabi-Yau manifold is, but there are special cases. And basically, Lidgeber studied one of these cases. This was a complete intersections in a product of weighted projective spaces. And they came up with this formula, which is sort of intriguing because it does involve zeta 3. So some of our favorite numbers. And I don't want to spend a whole lot of time explaining the notation. Basically, okay, on this side you got something purely topological. On this side you've got something with the Yukawa coupling and this a period function evaluated appropriately. Anyway, essentially what Lidgeber did in the paper I happened across was that he generalize this to higher dimensions. And you got a formula that involved this very intriguing multiplicative sequence for gamma of 1 plus t inverse, and then a sort of generalization of the preceding slide on the right-hand slide with this. And okay, again, I won't go into the technicalities, but again, this is some generalization of the Yukawa coupling. And I was just interested, is this really the same things that I've been studying? And well, sure enough, after looking at the paper for a while, I could prove the following theorem. The coefficient of the symmetric, of E sub lambda, this just means the product corresponding to the things in this partition, is just the image under this extension of M sub lambda. So this is the monomial quasi-symmetric, monomial symmetric function instead of the elementary symmetric function. And so this thing just sort of swapped elementary and monomial symmetric functions. And the proof is just one line. Of course, you have to know a little bit about symmetric functions. You have to know that the transition matrices between this basis for the symmetric functions and that basis are symmetric. But aside from that little thing, which is standard fact in the combinatorial literature, you get basically a one-line proof of this result. So then I could go back and see all his formulas in the paper, and actually there were some misprints in the paper, which I corrected. But and of course he's specializing to the Calabi-Yaw case, so the C1 is 0, and that's where you just get the lone zeta 3, because all this other stuff drops out. But anyway, was kind of neat. So I discovered this homomorphism had sort of an application in topology or mirror symmetry or something, which was quite unanticipated. All right, so now fast forward 10 years or so, and Rongmin Liu actually wound up considering the genus corresponding to this power series, which he called the gamma hat genus, and related to what he called the regularized S1 equivariant Euler class, which is some kind of infinite dimensional normal bundle or something like that. The point is a context that apparently had nothing to do with the mirror symmetry of Libgruber's construction, but it's the same sort of thing. And essentially all this is you kill off the gamma. So these are really just the same functions I had before, except set gamma to 0. So you could take all the formulas I had for the Q's and convert them, get formulas for Rongmin Liu's function by just setting gamma equal to 0, my previous formulas. So there's two applications in topology, which, again, quite unanticipated. Okay, so now I want to shift gears a little bit and talk about another aspect of this homomorphism. Because QSIM is not only an algebra, it's a Hopf algebra, which means you have a coproduct. The coproduct is just given by splitting this composition by juxtaposition. You sum over all possible juxtapositions that give you a given composition. And of course, this includes the empty one. Again, I've set M sub empty set equal to 1. So this really is a coproduct. Now, there's a theory of real characters of Hopf algebras. And as it happens, my extended zeta function here is a real character. That really just amounts to an algebra homomorphism. Now, a character is called even if it sends every even-dimensional element to -1 to the weight times. Sorry, it sends every homogeneous element to -1 to the dimension times chi of that. Of course, this says nothing. If the weight of W is even, it just says chi of W is chi of W. If you're working over characteristic 0, it says that chi of W is 0 if the weight of W is odd. Okay, and we call a character odd if it sends every homogeneous element to -1 to the weight times chi of the antipode applied to W. Again, if you know about Hopf algebras, you know that they have this gadget called an antipode. And that's my capital S. So there's a theorem due to Aguiar, Bergeron, and Satilla that says that if you have any real character of a Hopf algebra, you can uniquely factor it in the convolution algebra into an even character times an odd character, which means that there's a factorization of my extended zeta into even character, which I'm calling zeta plus, and an odd one, zeta minus. And to say that it's a product in the convolution algebra just says that when I apply it to any monomial, it's this sum, where the sum is, over the coproduct. Now remember, for monomial quasi-symmetric functions, that just means taking all the possible juxtapositions that give it. Okay, so that's their theorem, and as soon as I saw their paper, I started. They did it in a general way. As soon as I saw their paper, I started thinking, what does that say about my extended zeta? And it took me a little while to work this out, but okay, some things are sort of obvious. The primitives, now a primitive in a Hopf algebra is one whose coproduct is as simple as possible. It has to have these two terms. If there's nothing else, it's primitive. So the primitives in quasi-symmetric functions are just the power sums. And okay, so this zeta of I would just be zeta minus pi and zeta plus pi. But in fact, remember, the even part kills all the odd dimensional elements. So zeta plus a pi is just going to be zeta of I for I even, 0 for I odd. And because these things are primitive, the antipode just sends each power sum to its negative, which means that the negative part is going to kill all the odd ones and kill all the even ones, and the odd ones just go to themselves, with the understanding that P1 goes to Euler's constant. Okay, so that's all well and good. So just using this, I started computing away and making tables of what the factors do, these factored parts of the homomorphism do to various monomial quasi-symmetric functions. In fact, I worked it out completely through weight 6. And I found that it wasn't particularly simple. This fact, of course, is trivial. Zeta plus sends every odd dimensional thing to 0. But it was otherwise wasn't particularly nice, except for one thing that I noticed. It seemed that if all the parts of this composition were even, then the zeta minus part sent the thing to 0. So I actually gave a talk in 2006 in Leipzig where I stated this as a conjecture, and Marcelo Aguiar was there, and he pointed out to me that actually this was pretty easy to prove if I had just used this result that he and his student had proved earlier. And I had absolutely no excuse because, in fact, the student named Sam Sao had actually given a talk at the Naval Academy about a year earlier, and somehow I had missed this. But this is why it's good to go to conferences, to have people point these things out to you. So anyway, this is a theorem that if your composition I here consists entirely of even parts, then the odd part of the factorization just sends the thing to 0. But otherwise, these things are considered the general quasi-symmetric functions are not particularly nice. But things get dramatically different if you just work inside the symmetric functions. And by the way, for these sort of applications to topology I talked about, the gamma genus and the gamma hat genus, that's all you need. Because every monomial quasi-symmetric function is a polynomial with rational coefficients in the power sums. Okay, and so these things are homomorphisms, which means when I apply zeta minus to one of these, well, zeta minus, remember, kills all the even ones and sends the odd ones to gamma and then all the odd zetas. And gamma plus kills all the odd ones and sends the even zetas to themselves, or the even p's to the even zeta values. And so, in particular, this thing on the bottom is just going to be a rational multiple of power of pi, the appropriate power of pi. And these are going to be a little more interesting. But you can play around with the generating functions, and you get a rather nice result here. You see the involution of the algebra symmetric functions exchanging the e sub I and the h sub I just leaves the odd p sub I fixed. And so the elementary symmetric functions and the complete symmetric functions are going to look the same to this zeta sub minus, which is another way of expressing this is to say that the zeta minus of the ratio of the generating functions is going to be 1. On the other hand, zeta plus of e of t is an even function, which means that zeta plus is going to send e of t to the reciprocal of what zeta plus is going to do to the generating function of the complete symmetric functions. And so you get this formula for what zeta plus does to the ratio. And now use the fact that these, in the convolution algebra, give you this zeta originally, and you just have this little one-line computation that says zeta plus of h of t squared is gamma of 1 minus t times gamma of 1 plus t. Okay, well, there's a reflection formula for the gamma function that says that latter thing is just pi t over sine pi t. So you wind up with the following result, which I call the factor generating function, which says that zeta plus of e of t is the same as zeta plus of h of t inverse, which is the square root of sine of pi of t over pi of t. And zeta minus, the odd one, is the same as zeta minus of h of t is what it has to be for the product to come out right. All right, and then also you have this nice formula, which is classical, of course, expressing the elementary symmetric functions entirely in terms of the power sums. That's easily derived from just this generating function identity. Now, the cool thing about that, this does have these annoying minus signs all the way through. But if you apply the odd factor, zeta minus, to this, it turns out all the minus signs cancel out. And so you get this sort of neat formula. Of course, zeta minus kills all the even ones, so you just have the odd ones. And so you have this nice little formula for what zeta minus does to the elementary symmetric functions. And this is an example of how you could put this together to do a little computation. If you know the power series expansion of the square root of sine of pi t over pi t, and then you use the fact that the elementary functions in the Hoff algebra of symmetric function are divided powers, which means, okay, they're not primitive, but they're sort of the next best thing. You just have this string of elements like that. Then you can just apply this, to find the extended zeta of, say, E4. You use this expansion. Okay, so it's going to be taking odd of these, even of these times odd of those. But remember, the odd ones, the zeta sub minus is going to kill that and that. And so you wind up with half the terms dropping out. And for the ones where you apply zeta minus to an e, you can use the formula on the previous slide. For the ones where you apply zeta plus to e, you use this power series expansion. And so fairly quickly you produce this. So I found from all my calculations that I'd done earlier, although it's generally hard to evaluate the factors on the quasi-symmetric functions. On symmetric functions, it's quite easy. Anyway, I wrote this up some time ago for the Electronic Journal of Combinatorics. But now let me talk about some more recent work. It turns out that there are yet more changes to be run on this homomorphism. So instead of considering all multiple zeta values, suppose we just consider the ones in which all the arguments are even. Okay, so I'm going to introduce this quantity e sub 2nk. It's going to be the sum of all multiple zeta values with all even arguments such that these add up to 2n. Of course, if there's only one, then it's zeta of 2n. It's actually sort of implicit in Euler's paper from 1775 that if you just take the ones of length 2, they add up to 3/4 of zeta 2n. Not that he says it explicitly, but he gives formulas from which it follows easily. Nobody seems to have actually pointed out this identity in print until Gangle, Kaneko, and Zagier did in 2006. But last year, I happened across this paper by Shen and Kai, where they sort of extended this, and now they took like the length 3 ones, and they had to introduce another term. But the neat thing is these coefficients don't depend on n. So they had this nice formula for length 3 things of weight 2n with even arguments, and one for length 4. So I started looking at this last year, and well, when I see numbers like this, I just get hooked, and I started playing around, and a couple weeks later, I had this formula. And this happened when I was at Zeuthen last year. I mean, I was supposed to be looking at applications to multiple zeta values in physics, and what did I do? I proved this result, which is more about number theory. But you just never know how things are going to turn out. All right, so this is the correct generalization. Notice you have to sort of, every time this number goes up by 2, you have to bring in another term here. This is the floor function, so this is the greatest integer, k minus 1 over 2 here. Now, I won't say too much about the proof of that. That's an interesting story in itself, but what I want to talk about is how it relates to this generating function business. It turned out the key to proving this result is what I call the even multiple zeta values sum formula for here. That is, if you take the generating function of these numbers, 2-variable generating function of these numbers, it's actually quite easy to produce an explicit generating function. And a very nice one, too. This looks like that.
Excuse me, Mike, you have the zeta of 2j, but you kind of just turn it into pi to the 2j by dividing by b2.
Oh, I know. You could state this without Bernoulli numbers. And that's in my page. More natural. But I just wanted to write this in the same form that Shen and Kai had it here. Because what happened was, first I started looking at these numbers, and I saw the pattern of this quickly, so I sort of noticed right away what this number was. And then I sort of figured out what the formula would have to be for length 5, and then by then I was sort of hooked, so I sort of figured out the pattern of these coefficients, and so I had my result, and then I had to prove it, and I did this by using this generating function that I've written here. So it is a certain amount of work to get from this generating function to here. I'm not going to talk about that. I'm just going to talk about how you can get this generating function, because again, it's very, very nice. It kind of fits in with what I've talked about before. So now I'm going to go back into the world of just symmetric functions. So capital N sub nk will be the sum of all monomial symmetric functions corresponding partitions of n having length, partitions of n of length k. There's of length n that should be. Okay, so just partitions of a given weight having a particular length, which you don't usually think about. Of course, if you have the greatest possible length for a given weight, you get the elementary symmetric functions, because that's just 1, 1, 1, 1, 1, k times. And if your n is smaller than k, these are just 0. Now, this is exactly the gadget that my zeta function sends to this generating function e to the 2n k. And you can realize this in this d here is just the degree doubling function that takes all those basic variables xi and squares them. Of course, that has the effect of just sending the monomial quasi-symmetric function m sub I1 up to ik to m sub 2i up to 2k. And now I'm going to introduce a 2-variable function in the realm of symmetric functions. This will just be the thing that zeta d maps to my 2-variable generating function for the even sums. And so it'll just have these n sub nk's as coefficients. I don't have to bother with doing the extended one here because since I've doubled all the exponents, you know, I'm in Q0, sub 0 already. So, okay, so it turns out that if you take this symmetric function with these, where you take into account the length of the partition, it can be factored quite easily in the radiosymmetric functions. It's just the elementary symmetric function of s minus 1t times the complete symmetric function of t. And, okay, now I'm going to just apply the homomorphism zeta d to both sides of this. And, okay, you need to know what it does to elementary symmetric functions, but that's actually, I can mention my 1992 paper. I actually, in that paper, proved that the zeta of 22222 goes to zeta of 2n over 2n plus 1 factorial. And so that means that zeta d of e of t is just sinh of pi root t over pi root t. All right. Now, of course, remember that when you go from E elementary symmetric function generating function to complete symmetric generating function, you've got to take the reciprocal, replace t with minus t. Well, that means I've sort of got to replace the sinh with a sign, but okay. And so now, because of this factorization, I know what it does to each piece. I know what zeta d does to this generating function. And okay, again, I can, by changing signs here, I can get rid of the sinh and write it entirely in terms of signs. And that derivation was so neat and so quick, I actually had a little trouble believing it worked at first, but it does. And so you get this very, very slick generating function for these. And then, as I say, it takes another fair amount of work to get from here to there. But, of course, the thing is, I'd already conjectured this, so it was just a matter of figuring it out. And I had a few stumbles, but was able to do it. So that turns out you can get even more, a little more out of this. If instead of looking at this degree doubling homomorphism from the quasi-symmetric functions to themselves, you look at the d squared. So this takes xi to xi to the fourth. It means you take m sub I1 up to ik and you replace it with m sub 4i1. You can, it's again, going back to Borland, Bradley, Broadhurst, 1997, they don't write it quite this way, but you can write the generating function for what happens to this, the e of minus t that way. Well, if you know e of t or e of minus t, you know h of t, and therefore by using the same process I did here but applied to this more complicated gadget, you know what zeta of d squared of my generating function is. And okay, now you got both cinches and sines in it. Bit of a mess. And this is, I actually worked this out last summer too, because I was just playing around with the generating functions. But now Yuan and Zhao have actually used this generating function in a way analogous to the way I used this one to prove that. They used this generating function to get a formula for the sum of all multiple zeta values of fixed depth and weight 4n, in which all the arguments are divisible by 4 rather than 2. Now, it's about twice as complicated as this formula. It's actually a little more than twice as complicated because they sort of have some additional stuff in there. But it's one of these things where perhaps the surprising thing is that there's a nice formula at all. It's still a tractable formula. So this has appeared in the archive just within the last couple of months. Well, the question, in principle, yeah, but if you look at, well,
it's a product property. If you have, instead of 2 or 4, if you have 2 arguments, it's a product of the arguments.
Well, if you go back to this paper, yeah, but I mean the question is, can you write it sort of
It's a problem
nicely?
of signs with roots of unity. There are signs.
Right. But I mean, if you look back at this 1997 paper, that they're only halfway tractable up through about 6, and then these things get sort of horrible in a hurry. So
yeah, but there's a closed form. If you replace 2 or 4 by 2r, it's the same form with the product over the rth roots of unity. Of course, if r is bigger than 6, the rth roots of unity are actual numbers. But still,
right.
It's a closed formula.
It
doesn't matter.
Okay. But it's if you want a sort of nice formula, you sort of run out of steam around 6. And actually, Stanley has a paper in the Electronic Journal of Combinatorics from a couple of years back where he actually computes what happens to the Schur functions. And again, you sort of only get reasonable formulas up through 8.6. The roots of unity are just too messy beyond that. So I'm sure there's some more things you can do with generating functions, but that's where I'll end today.
Thank you. So we have lots of time for questions.
Yeah.
What a group theoretic meaning of quasi-symmetric quasi-symmetric functions? Is it?
I'm not sure if there's a group theoretic meaning. The paper by Ira Gessel, in which these were first defined, was really looking at them in a combinatorial context. And that's largely where they've appeared. There's a pretty extensive treatment of quasi-symmetric functions in the second volume of Stanley's book on combinatorial theory. But he works really in a combinatorial context, not a group theoretic one.
Naive question, what if you replace even by odd, you get something out of your factorization for MZV's odd arguments?
Yeah, if you go back to here and you want to do a sum where they're all odd, I think there's a result by Stephanie and Belcher about odd ones. I don't know a slick way to use generating functions there. Possibly there is one.
I have a question about Don's old 3-1-3-1-3-1-3-1 problem, which was eventually solved.
Yes.
Are there further identities of that kind that might yield to your piology?
That's something to think about. Admit I haven't thought about it. I think someone's.
Do these quasi-symmetric functions inspire how to choose a basis of higher depth multi-zetas at higher weight?
So the monomial ones really just correspond to the multiple zeta values themselves. Now there are other bases for the quasi-symmetric functions. And back when I was computing like crazy to find out what sort of zeta plus and zeta minus looked like, I played around with what they looked like in these other bases, but I didn't come up with any particular insights that one basis was particularly nice. You have, of course, there are symmetric functions I didn't mention. For example, the Schur functions. As I say, Stanley has a paper about what the images of some of the Schur functions look like. There are things that sort of correspond to this in the quasi-symmetric functions, but they're sort of more complicated. Things like ribbon Schur functions. Possibly one of those would give you a nice representation. But I struggled for a while when I was looking at this factorization, this Aguiar-Bergeron scintilla factorization. I didn't see anything particularly nice about those other bases.
More questions? I'd like to make two little remarks about connections with what you were talking about in physics. They're both rather amusing. One is that in the early days of quantum chromodynamics, there were two ways of renormalizing it after using dimensional regularization. One was called minimal subtraction, and the other was called modified minimal subtraction. And the first scheme, Euler's constant, appeared everywhere. People found this inconvenient. And the second scheme, which is the one we use now, Euler's constant doesn't appear. But the wonderful thing is the structure of the renormalization group is that a physicist using minimal subtraction can compare his or her results with someone using modified minimal subtraction just by multiplying their unit of mass by e to the power gamma.
Huh.
So that resonates very strongly with what you were saying.
It's kind of like a loose thing. Yeah.
And, you know, at conferences there was a discussion for a few months about what one should do. One decided that the formulas with gamma not equal to 0 were inconvenient, so they absorbed it. The other thing is that when I was working out the expansions in epsilon, the difference between the dimensionality of space-time, for progressively more and more difficult Feynman diagrams, to economize results, I found it very convenient to take the square root of gamma functions, just as you have been doing, yes? For the very good reason that I didn't want to put in tables involving useless pi squares that I could do down there. And the referee said, no one has ever taken the square root of a gamma function, and no one ever will. I did, and you've done. Okay, we thank Mike again.